Okay. So the differentiation in one variable function, if you have one variable function, right? The notation used d by dx, d, right? But here, this is partial, right? This is the red one is partial one, right? So when you have one variable, one independent variable x, so dy by dx, or you can write it dy by dx. Some people use it y dash of x is the same thing, right? So the result of this one give you what? Give you the slope of the tangent of the curve y equal to f of x. This is the meaning of the derivative, right? So you know how to find the slope of the tangent of any curve given by y equal to f of x, right? Okay. What does it mean partial f bar partial x in the multivariable function? It is also the slope, but it is one of the coordinate of the slope, right? Okay. So here we call the tangent slope is a vector. Is what? A vector, right? So what we call it? We call it grade f, right? Or q or whatever. Call it as you like. Okay. But remember, your function is not in one variable. It is in n variable, right? So what is grade? What does it mean grade? Grade is called nabla f. What's nabla? Nabla is the derivative, partial derivative vector. What is I? As you know, if we have two dimension, we have unit vector I in the direction of x and another unit vector in the direction of y, call it j, right? If we are in 3-dimension, we have 3 unit vector, right? I, j, k. So this is exactly the unit vector, right? So here, if we have many, right, we say partial by partial x1 in the direction, let's go for 2 variables just to make it easy for you, right? If we are in the 2 variables, so plus partial by partial y in the direction of j. If you are in 3 variable, you have another variable z in the direction of k. So you can write this one as a vector, right? You can write it as a vector, partial by partial x, partial by partial y, partial by partial z. So sometimes they write the vector in this way, and sometimes they write it in this way, right? Okay. Sometimes you cannot multiply this one, so they write t. What does it mean, t? T, it means transpose, right? Transpose, it means the first one will be the first one, the second one will be the second one, the third one will be the third one, but in a row, not in a column, right? Okay. This is exactly equivalent to the slope in the partial derivative in the multivariable. And here we are talking in 3-dimension. We are talking in what? In 3-dimension. How to differentiate in the partial derivative exactly like how you did in the one variable function, right? Let's go for one example, right? If I go for one variable, so you can write f of x equal to x cubed minus x squared plus 3. So you would like to find the first derivative, right? So you need f dash of x, or you can write it d by dx for f, right? What is the rule for x to the power n? You take the power down and you subtract 1 from the power, right? Yeah, on minus 2x, and any constant has a derivative 0, right? So this is the first derivative. This is what? First derivative. What is the second derivative? The second derivative is the derivative of the first one, right? So differentiate again. Minus 2. Excellent. Great, great. Now this is the second derivative, and you can carry on, right? Let's go for the multivariable function, right? Let's go for function of x, two variable x and y, right? Say x cube y minus y cube x plus 3x square. How many first derivative you have? You cannot write f dash here, right? We will talk about it later. We go for partial derivative with respect to x and partial derivative with respect to y, right? So here you have only one, right? Because you have only one variable, right? One variable function. But if here you have what? Two variable function. So you have two first derivative, right? Two first derivative. Can you differentiate? Yes, I can differentiate. If I'm differentiating with respect to x, I keep y as a constant, right? So when I differentiate this one, I keep y as a constant. So leave y as it is, take it outside, and differentiate x cubed with respect to x, it will be 3x squared. Easy? When I go differentiate with respect to x, I consider y as a constant. The derivative of any constant is good. Now I go differentiate with respect to x. So I have to the power down, multiply by 3 will be 6, and subtract 1 from the power. So I have x to the power 1, right? Now I can write it down in a nice way. So it will be 3x squared y plus 6x. This is the first derivative with respect to what? X. Can you do for y, please? No. Here? Yeah, you keep x as it is, right? You are right. And the last part? Excellent. So you can write it as x cubed minus 3x y squared because we used to write x first. Okay, so that's it. Now we know how to differentiate with respect to any variable, right? Okay, let's go for the second derivative. Yeah, what is the second derivative here? I have only one, right? But here, how many second derivative? Again, I have second derivative with respect to x. Okay, I have second derivative with respect to y, and I have one mix, right? I have one mix between x and y. So you have x and y. It is the same as if you differentiate with respect to y first and then differentiate with respect to x, right? It doesn't matter. You start with x or you start with y, right? It will be the same. Okay. Now, how to find the second derivative? For sure, as we have done here, we get the second derivative from the first one, right? We will do the same thing here. So I'm going to differentiate what I differentiate with respect to x again, right? So I'll come here and differentiate again with respect to x. And be careful, when you respect to x, y is constant, right? So what is the second derivative? 6xy plus, excellent, brilliant. The second one, you go for the derivative of y, right? So you take this one to here. Yeah, yeah. You differentiate with respect to y, so you have to consider x as a constant. Yeah, mistake is good. You will learn from it. 0. Yeah, it's better to write 0 to remind yourself, right? Yeah. Yeah. So mine. Yeah, it's okay. So it is equal to minus 6xy, right? Let's go for here. For this one, it is up to you. You start from x and then differentiate with respect to y, or start from y and differentiate with respect to x. You have the same result, right? Let's go for this one. We differentiated with respect to y and differentiated with respect to x to have this one. So how much you have? This one. You differentiated with respect to what? So you need to differentiate it with respect to what? X. Okay. Yeah, it doesn't matter. If you start from here, it doesn't matter. No. Okay, if you start from here, you finish x, right? Take the result and differentiate with respect to y, right? If you start from here, you finish the derivative with respect to y and do it for x. Okay, yeah. Yep. Yeah. 6. This one. You finish y, so you differentiate. It's up to you if you start with this one or start with this one. It's up to you. Which one? Which one you will go for? Partial. Partial f by partial x. This one, right? You need here, if you finish the derivative with respect to y, do it for x, the result for x. If you finish it for x, make the result differentiation with respect to y, right? So it is up to you. If you start with this one, that's fine. If you start with this one, also fine. So what do you have? You've here, yeah, if you finish with respect to x here, you do the result with respect to y, right? So I will take this one and differentiate it with respect to what? To y, right. So what do you have? Excellent. Excellent. Very good. That's good. Now, you know, here you have only 1 second derivative in the ordinary differentiation, but in the partial one, you have 3, right? Supposed to have 4, to be honest, Alan. But these two are equal, right? Yeah, this one. Yeah. It's the same answer. If you don't believe me, you can start from this one and differentiate with respect to x. You will have the same result, okay? Now we know how to distinguish between one variable function derivative and multivariable function derivative, right? And also we know what does it mean nabla, right? Which is, they call it the grade of the function. So nabla is a vector, is a derivative for each component of f, right? Okay, if I have this one, I call it a scalar function. We call it what? Scalar function. Okay, good. Sometimes you have a vector function, right? So sometimes you have a vector function. Vector function. So what is the difference between the scalar and the vector? When you have a vector, you should have a unit vector, right? If you are in two variable here, so your function here, let's call it z, because when you have z, it means you have z as a function of the two variable, right? So you have first component of x and y, and you have a second component of x and y. So this one we call it what? Vector function in 2 dimension, right? If you have w as a function of 3 variable, x, y, z, so yeah, good. So far, so good, Alan. It's good. How many components here, Alan? You have 3 components. Maybe one of them is 0, right? It doesn't matter. But at least I know that we have 3 components. If any one of 0, I don't care. Now, what is the difference between nabla when affect on is a scalar function and nabla when a scalar affect or act on a vector function? Here, when you have a vector function, we write it down as f capital and hat like this one, right? Okay. So this vector function, we can write it like this one. So when you have 2 vector, because I know nabla is a vector, right? And f is a vector. Between them, you may have 2 type of multiplication, right? One of them, they call it the scalar multiplication. They call it what? Or dot product, right? Or scalar product. Okay. So how you can multiply this one? Okay. I know nabla. If I'm talking about, let's go for the 2 dimension, right? Or 3 dimension, doesn't matter. So partial by partial x I plus partial by partial y j partial by partial z k. This vector will be multiplied in a dot product by my function. If I go for 2 dimension, how many I should stop here, right? This is 2 dimension, right? If I go for 3 dimension, here the 3 dimension, right? So if I have 2 dimension, I have 2 components, right? If I have 3 dimension, I have 3 1. So I go for the 3 1. How to do the dot product? They call it a scalar. Why they call it scalar? Because the result is a scalar. It's not a vector, right? Because when I multiply I times I, it give you 1. J times J give you 1. K times K is 1, right? So remember, the unit vector, when they are the same, the result is what? Is 1, right? Catch the point? But if they are different, I dot j will have 0. Why it is 0? Because they are perpendicular, right? Because any 2 vector perpendicular has no angle between them. They have angle, right angle, right? Okay, this is why the dot product, if I said A as a vector times B as a vector, is exactly the absolute value of A, or the length of the vector, times B, and then cosine theta. And theta is the angle between A and B, right? This is the scalar multiplication definition, right? So this is theta. When theta is pi over 2, Alan, so it is fair enough the scalar multiplication will be what? 0, right? And I know I and j are perpendicular. I and k are also perpendicular, so it is 0. Also, I and j, yeah, j and k, yeah, dot is 0. But only having 1 when the same vector multiplied by the same one, right? When you multiply the same vector, right? If you multiply k by itself, give you 1. J by itself, give you 1. But if you have another one, you will get 0. Why? Because this is the scalar multiplication. It's the length of A, length of B, cosine theta, Theta is the angle between them. If they are perpendicular, because here, when I have ijk, I know all of them are perpendicular, right? Now you know how to find the multiplication here. So it will be partial by partial x for the first component plus partial by partial y by the second component, partial. Yes, partial by partial z for the third component, right? This is what, Alan? This is the scalar multiplication for nabla and the three variable vector function, right? Catch my point? I think now you know how to handle nabla in the grade. This is what do they call it? What they call this one? We know nabla with the scalar one, we call it grade. This one we call it what? Nabla.f. We call it what? Okay, yeah, I will go for this one. Yeah, gradient of the, okay. So the difference of the gradient of the scalar is a vector, but the gradient, this is not a, the gradient for the vector is a scalar, right? Okay, you have another multiplication. Do you remember this one? Nabla cross f, right? Do you remember this one? This is, we call it curl, right? Curl. Curl. Okay, I will let you know. Okay, I will let you know. If you have f is here and nabla is here, f cross nabla is perpendicular over both of them, right? So this one will be, this will be nabla cross f. So this is a perpendicular vector over f, right? So this one is exactly I, j, k, and both the component of nabla is here, and put the component of the your function here. Find the determinant of this one, okay? You find the curl of f, right? If you don't hear about it, just leave it for now, okay? You know how to find the determinant? Yeah, you just fix the column and the row, and then multiply this one by this one, and you have to apply the sign rule. You have plus, minus, plus, right? So you multiply this two, so partial by partial y f3 minus partial by partial z f2 will be in the direction of I, and then minus, I have another one j, fix the j column and the row, partial by partial x for f3 minus partial by partial z for f1, partial by partial z f1. The last one is a k1. You fix the k column and row, partial by partial x for f2 minus partial by partial z f1. Get it? So this is how to find the determinant for this one. This is the names of nabla with the scalar, we call it gradient, with the vector. I'm sure there is another name for this one. I don't remember now, but anyway, for nabla dot f. No, the name. It is. This is a called curl. This one, I'm not sure about this name. I forget it now. And with the scalar multiplication function, we call it gradient f, right? But we can say, yeah, that product. It has a name anyway. I will let you know later on. Now we know how to differentiate in the ordinary differentiation and with the partial derivative, right? So you have to know the rules for all functions, right? And now we know how to find the gradient, right? Okay, and let's go. Do you remember the local maximum and local minimum, right? Don't worry, don't worry, don't worry. We have this one only for one variable function, right? We don't have the third one. I will show it to you now. Let's go for how to find this one. To be honest, they call it stationary point. They call it what? Because it's like a station, you know, you have to stop in there. Right? Okay. What does it mean? It means your function is going up. So this is a local maximum, right? And if you go down and go up again, this is what? Local minimum, right? This is what does it mean, local minimum, local maximum, right? Okay. You have another point when you change from up and down. Yeah, look at this one, going like this one, and then you go up like this one. So when your curve, it changed, this is, they call it inflection point. They call it what? Inflection point, right? You don't have this one in the three dimension, right? How to find this one? How to find the local maximum in one variable function? It is easy to find the point, to find the stationary point. Could be one or could be more than one, right? So how to find them? You find them from the first derivative. You have to put df by dx equal to 0, right? Okay. Solve it. Solve with respect to x. You find the value of x, right? If you have one, that's okay. If you have more than one, that's fine. Okay? The next step, how to check this one? You check this one, check it, local maximum or local minimum, right? If the second derivative, look at this one, the second derivative at x equal to x1, say, right, is positive, we call it local minimum, right? If it is the opposite way, if the second derivative in another point, d by dx squared, in the second point, x equal to x2 is less than 0, you call it what? Local maximum. Catch it? This is how to find the stationary, and this is how to check it, right? Finish? Example? For sure, it's easy, easy, easy. Okay, find the stationary point, maybe more than one, and classify them. Okay. So now let's go for f of x or y equal x cube minus 3x squared plus I would like to have a point here. Just make this one plus. So I have 6 Okay. Let's go. 5x. I will let you know why I bought this one. Okay. Solution. Yeah. Y minus plus 6x plus 5. And you put it equal to what? Yeah. So do you have your calculator, or you are not allowed to use a calculator? Okay. Let's make it easy. Let's make it easy. I will change this one just to make it easy for you. Right? So we'll cancel out this one with this one just to make it easy for you, right? So now, if you are allowed to use a calculator, that's fine. If not, you have the 2 bracket. You are lucky because this is a prime number, so you have only 5 times 1, right? And this is positive, so both of these two numbers will take the sign of the middle one, right? So plus and plus, here is x, right? Equal to 0. From this one, x equal plus 1 equal to 0 implies to x equal to minus 1. This is my first one, x1 I call it, right? The second one, x plus 5 equal to 0. Yep, x2 will be negative 5. How to check them? I have to find the second derivative, right? So to check, find what? D square f by dx square. Let's go. So I end up here, right? So I have to differentiate this one again, right? So the derivative of x squared is plus 6, right? Now we are going to check. We have 2 points, right? X equal to minus 1 and x equal to minus 5. If I have x equal to minus 1, the second derivative at x equal to minus 1 equal to what? 2 times minus 1 plus 6 equal to what? 4. I don't care about 4. I'm caring it is positive, right? So this one is the local maximum. X equal to minus 1 local maximum. Okay. Now for this one, d square f by dx square when x equal to minus 5 is 2 minus 5 plus 6 equal to minus 4. It is negative, so x equal to minus 5 is the local maximum. Catch it? Easy? The same thing you will do in the multivariable function, right? Okay, so now we'll take the other parts here, but we have to add something here. They call it the saddle point. We call it what? You know the horse? The thing you put it in the back of the horse is called saddle, right? Yeah, so this is the saddle point. This is only in 2 dimension, right? Or 3 dimension? 3 dimension, right? So the saddle point is only for 3 dimension, right? So I should have a function of how many of 2 variable, right? Because we call it z equal to it. So I have 3 dimension. One for x, one for y, and one for the function, right? So saddle point is not in 1 variable function, right? Inflection point is here How to find the inflection point? The inflection point when you put d square f by dx square equal to 0. This is to find the inflection point, right? You just put the second derivative equal to 0 and find x, and that's it. No need to check. Catch it? We don't have here inflection point, but we have another one distinguish the 3-dimension or the 2-variable function called the saddle point, right? Also, let's go for the local minimum, local maximum. You have something called Jacobian. I think you hear this name, right? And you heard about Hessian or Hessian, it depends. Hessian matrix, right? The Jacobian is the determinant of the Hessian matrix, right? If we call this one H, so the Jacobian is the determinant of H. I know very confusing names, but at least you know what is going on, right? What is the Hessian matrix here? The Hessian matrix here is partial by partial, partial square by partial x square. In here, partial s by partial y square. And in the other corner here, you have partial square by partial x partial y, right? And here you have partial square. You can leave it as it is, or you can make it partial y partial x. I know this is symmetric. Why it is symmetric? Because this one are the same, right? This is why they call it is symmetric. Okay? So Hessian matrix or Hessian matrix is a symmetric, right? But here the partial square, partial x, partial y, and here partial square, partial y, partial x, because they are equal. This is why this one is equal to 1. In general, Alan, symmetric matrix, the matrix A is symmetric when Aij equal to Aji. It means the element in the row I and column J is the same as the one in the row J and column I, right? Okay, this is a Hessian matrix in a very quick, right? The Jacobian will be the determinant of this one. So the Jacobian will be partial s by partial x squared. And here, no, for 2D, no, because you don't have, in 2D, you have one variable function. Because here, in you have x, your independent variable, and here you have y, and you know y is your function, right? In the 3-dimension, yeah, that's good to discuss x and y, and here is z, which is your function, right? Good. Now, you know the main diagonal here. The main diagonal is a second derivative with respect to x and y, but the other diagonal is the second derivative, once for x, one for y, and here you can have it. And you know that this is R equal in the 3-dimension. So this is a Jacobian. Now, what is the link between Hessian matrix, right, and the Jacobian, and what we are talking about, the stationary point, right? We have to link them, right? So if you have the Hessian matrix is positive, definite. This is a new definition here. What does it mean, positive definite, Alan? The determinant, the determinant is positive, right? When you have the determinant positive, this is what does it mean, positive definite, right? Well, and then you know it is negative definite when what? The Jacobian or the determinant of the Hessian. Yep, good. When you have this one, this is, they call it the saddle point. They call it what? Saddle point. So saddle point has one condition, right? How to write this one instead of h? Because if you have this one, how to find the determinant here? You multiply this one by this one and subtract this one, right? So if you have a function f or z or whatever, so you can write here partial square f by partial x square multiplied by partial s square f by partial y square minus partial square f by partial x partial y, because I know they are the same, so it will be square, right? So this is the Jacobian. So you can write partial s square f by partial x square multiplied by partial square f by partial y square minus partial square f partial x partial y, and here is what? Square is positive, right? You need here, in this case, you have, if you have this one positive definite, you have two cases here, right? One of them local maximum. This is happen when what? Fxx is negative. Yeah, less than 0, right? And local, yep, maximum when Fxx, can we check? I will check with you. 0, right? Okay. Yeah, because both of them you check by Fxx. You don't care about Fyy, right? If you have the Jacobian or the H, the Hessian matrix, or this part is positive, you have the two sides, maybe local maximum or, sorry, I wrote it twice. I'm sorry. I know you why you confused. Local what? Local minimum. Sorry. Yep, sorry. I'm sorry. Catch my point? Good. Now you follow the same technique, right? You have the second derivative. Okay. How to find the stationary point? Exactly like what you have done here, right? You put the first derivative equal to 0, right? So to find the stationary point, how many first derivative you have? How many first derivative? No, you have two because you are in three dimension. Yeah, good. So similar to this one, as you have done in one dimension, you will do in the two dimension. You put the first derivative with respect to x equal to 0 and partial f by partial y equal to 0. You have to solve this one simultaneously, right? If you are allowed to use your calculator, you will be lucky because it will be easy for you, right? How to check? This is how to check. Let's go for one example. Let's go for one we learned, right? We are looking for compute gradient nabla for all x, y. Let's go. What does it mean, nabla f? Partial f by partial x plus partial f by partial y. Don't forget here you have what? I, j, partial f by partial. We have only two, right? So I will stop in the second one, right? Let's go for one by one. Partial by partial x. Go and differentiate this one with respect to x, Alan. So what? For x minus y square. Brilliant. Brilliant. This is in the direction of I plus, okay. Now differentiate with respect to y. Excellent. To xy, if it is possible to do it. And you have to put this one between bracket because the unit vector must be outside, right? So we finish the gradient, right? Easy to find the gradient. Now let's go for the Hessian matrix. What is the Hessian matrix? H. Do you remember? This is a matrix, right? Okay, don't worry, don't worry. Partial by partial x here, square, right? Here, x square, partial square by partial y square here, partial square here if you have f. So it is easy to write f, straightforward. Okay. We have done most of it because you already differentiate, right? Okay, now you need the second derivative, Alan, right? With respect to x. This is what? This is the derivative with respect to x. So differentiate again with respect to x. What do you have? Excellent. So we have 4. Sorry. So we have 4. Now, let's go for the second one also to be easy for you. This is the derivative with respect to y, right? Differentiate again with respect to 2 minus 2x. Excellent. Now, as I told you, go for this one and differentiate it with respect to y because you already finished x. If you differentiate with respect to y, what do you have, Alan? No, this is for 0 for this one, but not for this one. So I said this is symmetric, so no need to do this one again because symmetric, it means the one in the first row and second column is equal to the first row, second row, and first column, right? Now we finish. We finish Hessian matrix. This is a Hessian matrix, right? So this is section B. This is section C. What else? Shows that 0, 0 is a stationary point. We know what does it mean, stationary point, right? How to find the stationary point? We find partial f by partial x, put it equal to 0, and partial f by partial y equal to 0. This is, so this one give you what here? What is partial f by partial x? Here it is, right? So 4x minus y square equal to 0. And the second one? How to solve this one? Are you allowed to use a calculator? Even if you are allowed to use a calculator, you cannot solve these two because in the calculator you are allowed to for a linear equation, right? So it is easy to call this one 1 and call this one 2, right? So from 1, what do you have from 1? You can get 4x equal to y square, right? So x will equal to y square over 4. Substitute in 2, right? I'm going to replace x by y square over 4, right? So what do you have? You have 2y minus, I replace x by y square over 4y, right? Equal to what? 0. Now I cancel out this one with this one. I have 2. Multiply by 2. Multiply by 2. So you have 4y minus y cube equal to what? 0. I can take y as a common factor. So I have 4 minus y square equal to what? 0, right? Now, this one give you what? Y equal to what? 0. This one give you what? 4 minus y square equal to 0. It means 4 equal to y square. It means y equal to plus or minus what? 2, right? So what's your points? How many points you have? 3. If y is 0, x equal to what? X equal to what? 0. If y equal to 2, x equal to what? This is the relation between x and 1. No, this is x equal to y squared over 4. So you have x equal to 1, right? If y is equal to minus 2, also x is equal to 1, right? Because this is a relation between x and y here. Got it? Just take your time. Take your time. From up to here, do you have any problem up to here? Okay. Go for number 1 and move this one to the other side, right? This is what I have done. Yeah. So I have x alone. X will equal to what? Y squared over 4, right? I would like to substitute in number 2, right? Here, right? So 2y, I get x and replace it by y squared over 4, right? And y. I replace x by y squared over 4, right? This is x, right? Right? So I cancel out 2 with 4, so I have 2, right? I would like to get rid of this one, so I multiply 2 in both sides, right? So this one will be coming what? 4, right? And this 2 will be cancelled out, right? And y squared times y is y cubed, right? Okay. Now, how to find this one? You factorize this one, so you take y as a common factor. So you still have y 4 minus y squared, right? If you have a multiplication equal to 0, it means each part is 0, right? Y equal to 0, I finish it. So I have to find x. I find x from the relation between x and y here, right? If y is 0, x will 0, right? For this one, you have 2 value of y, right? And you have the relation between y and x again, right? For this relation, if you have y equal to positive 2, x will be 1, right? And if y is minus 2, when you square any negative, it will be positive, right? So you have positive 4 over positive 4, you have also x equal to 1, right? So how many points you have? 1, 2, 3, right? So you have 3 points to check. Okay, the first thing I have to check is the Jacobian, right? Which is, what is the value of this one? Okay. Add the point. One of them, 0 and 0, right? Let's go one by one, right? So where is the second derivative? You have it here, right? Yeah, it is easy to have this one from here. So you multiply this one by this one, right? You multiply this one by this one and this one by this one, right? So you will have 4 times 2 minus 2x minus, so you have minus 4y squared, right? Because I know this is exactly what I need, right? This is exactly what I need. I multiply this one by this one minus this one by this one, right? So I have the value already here, right? So I call this one, the determinant of this one, I call it the Jacobian, right? So instead of differentiating again and waste my time, he asked me in section C to have the Hessian matrix, right? So the determinant of the Hessian matrix is the one I'm looking for, this one to check, right? To check, I have to use the Jacobian of the Hessian matrix, right? At the point x, say x naught and y naught, right? So I have to check, is it positive, negative, or negative definite, right? Okay, let's go for 0 and 0. If you have 0 and 0, x is 0 and y is 0, what do you have here? X is 0, 0, so you end up with 8, right? So you have 8. I don't care about the value, I'm caring this is 1. So you have two options here, maybe local, maybe minimum, or maybe local maximum, right? Now I know it is positive definite, right? No, I have to check fxx, right? So fxx is my partial x f by x squared at the same point, 0 and 0, right? What is my partial square f by partial x squared? I have done it, so I'm not going to waste my time again. It's supposed to be in this one, right? Which is equal to what? No x, no y, so no need to substitute, right? It is already, for all values of x and y, it is 4. So it is what? Yeah, excellent. So 0 and 0 is a local minimum. So in the second derivative, fx is positive, minimum. Fxx negative, maximum. Now do you don't have any suspicions, right? Good. I will leave the other 3 points for you, right? So now you can do the other 3 points, right? X equal to 1 and y equal to 2. Yeah, the second point, you take the same value here because this one is coming from this one when you multiply the main diagonal and subtract the multiplication of the other diagonal, right? So you already have the value of this one in terms of x and y, right? So no need to do it again, right? You will take this one, and instead of 0 and 0, you take x equal to 1 and y equal to 2 once, and the second time you check this one, right? Because you guarantee the second derivative is positive, right? But I would like to check, the Hessian Jacobian, right, is positive definite or negative definite, right? Okay. Now I'll go for this one. I go for the partial square f by partial x squared times a partial x by partial y squared minus partial square f by partial x partial y squared at the other point, right? Which is x equal to 1 and y equal to 2, right? I know this value, already I have it from my Hessian matrix here, right? So no need to do it again. So 4, 2 minus 2x minus 4y squared. And I plug in x by 1 and y by 2, right? So how much is it? If you have 1 here, so this is 0, right? And negative, right? Yep, this is negative 6. I don't care about the 16. I'm caring about this negative, right? Yeah, so I will make the negative by the red one and 60. Because it is negative, so it is saddle point, right? So 1 and 2 is a saddle point. Easy? Let's go for the third one. Y equal to minus 2. Okay. So again, y equal to minus 2. So I go to calculate this one. I'm trying to write it many times just to remember it, right? X equal to what? 1 and y equal to minus 2, right? Okay. Now I know this value is what? It's this one, right? This one or that one or the one I got it from the Hessian matrix, determinant of the Hessian matrix is the one I'm looking for. This is the Hessian matrix, right? The Jacobian is the determinant of the Hessian matrix, right? So it is the determinant of 4 minus 2y minus 2y, and here you have 2 minus 2x. How to find the determinant? Multiply this one by this one and subtract this one. So you have 4, 2 minus 2x minus 2 and minus 4y squared. Catch it? He didn't ask me for the Jacobian here, but he asked me about the stationary point because I have to define the value of the Jacobian at each point, right? If x, which is it 4, 2 minus 2x minus 4y squared at x equal to 1 and y equal to minus 2. I said when x equal to 1, this is what? This is 0, right? So if y is equal to minus 2, it's still minus 16, right? So this one is negative definite, right? So the Hessian matrix is a negative definite. So 1 and minus 2 is also a saddle point, right? Unless we have a mistake. Saddle point. It is easy now to find the stationary point in one variable and in two variable. How to check local minimum, local maximum, and inflection point in one dimension, or one variable, sorry. And in the two variable, how to check local minimum, local maximum, or saddle point. Easy. You know how to find the Hessian matrix, how to find the Jacobian. What does it mean, positive, negative, and positive definite and negative definite? Okay,